Numerical simulation of the Korteweg de Vries equation with machine learning. Welcome to Journal Club. The latest academic research, explained in plain English. Today we're looking at this paper from MDPI's Journal of Mathematics. It's authored by Williams, et al., from the Air Force Institute of Technology in the United States, and is published open access under a CC BY license. Let's start by translating the title into more accessible language. When you read this title, you can understand it to mean in very simple terms that this paper explains how to use a computer program and artificial intelligence to solve a mathematical equation called the Korteweg de Vries equation. Let's expand on that a little. This paper is about using computers and machine learning to simulate a mathematical equation called the Korteweg de Vries equation. This equation is used to study waves and how they move in a certain type of fluid. By simulating this equation with computers and machine learning, scientists can better understand how waves behave and predict their movements in real life. Now we understand the title, which is a good start, but before we can break down the full paper, we'll need to catch up on some terminology, jargon, background information and context. Specifically, there are some key concepts you'll need to be familiar with. Let's define them now. Numerical simulation. Developing computational models to imitate real-world phenomena. Korteweg de Vries equation. A mathematical equation used to describe certain types of waves. Machine learning. A technique in artificial intelligence that allows computers to learn from data without explicit programming. Nonlinear wave equations. Mathematical equations that describe the motion of waves in a nonlinear medium. Discretization, a method used to represent continuous processes with a finite set of values. Truncation error, the difference between the exact solution and a numerical approximation. Centered finite differences, a numerical method used to approximate the derivative of a function. Implicit-explicit time solver, a numerical method used to solve differential equations. Symmetry conditions, a set of conditions imposed on a problem to ensure that the solution is stable and accurate. Spectral methods, a class of numerical methods that approximate a function with a sum of sinusoidal functions. Now that we understand the title and key concepts, we're ready to dive in and break down this paper. In this presentation, we're going to attempt to answer 5 questions. 1. What were the researchers trying to figure out? Or more specifically, what was their hypothesis? 2. How did they conduct their experiment? That is, how did they test their hypothesis? 3. What were the results of the experiment? 4. What conclusions did the authors draw from those results? And lastly, 5. Why does this research matter? Why should you care? 1. What were the researchers trying to figure out? The researchers hypothesized that a machine learning procedure could be used to create accurate numerical schemes for solving nonlinear wave equations on coarse grids, using the Korteweg de Vries equation as a test case. 2. How did they conduct their experiment? The researchers generated both training and testing data for their study using highly resolved numerical simulations, using Fourier collocation for spatial derivatives and an IMAX 2-time stepping scheme. They used a machine learning model solely for the linear spatial derivative term, which was constructed using a finite difference method for the third derivative term, which was then substituted by an approximation derived from the machine learning model. The objective function used for training was the truncation error of the approximation, evaluated using highly resolved numerical simulations as a proxy for the exact solution. The weights of the model were optimized via steepest descent, and once the optimized weights were found, they were used to evaluate new initial data and compare to finite difference and Fourier collocation using the same time stepper and spatial discretization. 3. What were the results? The researchers' model was able to predict the behavior of the equation accurately, even for longer periods of time. Additionally, the researchers tested the model on 2 sets of initial data simultaneously, which allowed the algorithm to find the optimal coefficients that minimized both sets of data simultaneously. Overall, the findings suggest that machine learning can be a useful tool for simulating complex equations like Korteweg de Vries. 4. What conclusions did the authors draw from their results? The researchers found that they could use machine learning to optimize the coefficients of a numerical differencing scheme for the KdV equation. The scheme they created, trained on a coarse grid, outperformed 2 classical methods. The methodology they use can be applied to other nonlinear wave equations. Future work could include using the forward error as the objective function, training the model on non-consecutive time steps, adding more layers to the model, and using a different activation function. 5. Why does this research matter? This research paper is important because it proposes a new method for creating numerical schemes for solutions of nonlinear wave equations on coarse grids using machine learning. Moreover, the methodology is expected to be applicable to other nonlinear wave equations. Overall, this research has significant implications for the fields of computational physics and machine learning. We hope you've enjoyed this Journal Club presentation of numerical simulation of the Korteweg de Vries equation with machine learning. If you'd like to read the full paper yourself, which we encourage you to do, you can find it at DOI 10.3390/math111329791.